Welcome back to the HPL seminar. Thank you for joining us today. All right, it's my pleasure today to introduce our speaker, Jonah Dimnik, who is currently a master's student here at the University of Calgary, working within both the Human Performance Lab and the McKay Institute for Bone and Joint Health, and he is under the supervision of Dr. Brent Edwards. Jonah's academic journey began with a bachelor's degree in mechanical engineering, also here at the University of Calgary, where he developed a continuum damage model of fatigue and failure in whole bone for his undergraduate thesis project. And now, as part of his MSc in kinesiology, he continues to explore bone mechanics using advanced computational modeling techniques. And beyond his research, Jonah enjoys training service dogs and coaching youth football. Hopefully he's not getting those two mixed up. Teaching a linebacker to sit and stay may not be going very well. For his presentation today, he will be talking about computed tomography-based finite element modeling of the rabbit hindlimb.
Wonderful, wonderful. Thank you very much for the introduction. I'll kind of jump right into things here. So every time that we walk, run, or jump, we place the bones of our body under some of this mechanical loading. And this here is just an example of that. So we have this runner with every stride that he takes, he generates some of that ground reaction force, some of that's transferred up through the foot and into the tibia. So we can take a bit of a closer look into the tibia here. We have a cross section of that cortical bone. So this running is an example of this repetitive submaximal loading. So no individual step that this person takes is very likely to break their bone entirely, but what it will do is it'll lead to this accumulation of micro damage. And that micro damage, we can see some of these cracks and voids there on this image. And the physical manifestation is in the form of these microscale cracks and voids exactly like this. And the micro damage can begin to coalesce, eventually initiating a crack, and that crack can propagate further and further until we reach a point of complete bone fracture. And this is where we see stress fractures clinically. So it's a mechanical fatigue phenomenon. And we know that this is a very simplified process. This isn't the whole story that takes place in bone. Bone is a very highly dynamic biological tissue, and it adapts to this loading environment primarily through two processes. So we have bone modeling, where the bone adapts its size and shape to resist future loading. And then we have bone remodeling, where this is partly involved in the bone turnover process and mineral homeostasis, but also works to remove and replace some of this old damaged bone as well. So I'll talk a little bit more specifically about this bone remodeling process here. So over there on the left-hand side of the screen, we're looking at another cross-section of cortical bone, and you can see all these individual osteons that make up that cortical bone. And the osteon is the structural and functional units of cortical bone. So here on the left, we're now looking at a cross-section of an individual osteon. So I'm talking about specifically intracortical or eversion remodeling. This is the predominant form of remodeling that you'll see in human cortical bone. So bone remodeling takes place through this coupled sequential action of our osteoclasts here and our osteoblasts. And together, those osteoclasts and osteoblasts form what's called the basic multicellular unit, or a BMU. So in this image here, we have the BMU is propagating towards the left in your screen. So those osteoclasts are in front, and then our osteoblasts there behind it. And talking more specifically on the osteoclasts first. So again, they're at the front of what we would call the cutting cone. And their job is to go ahead and remove or resorb this old damaged bone. And then following in behind this cutting cone are those osteoblasts, these guys in green. And their job is to come in and fill in that cavity with new, healthy, mineralized bone material. So now we can talk about how bone responds to mechanical loading. So I'll go through a bit of a conceptual framework. This is what you'll typically find in either textbook or in the literature on this topic. So we undergo some bouts of mechanical loading, and that mechanical loading acts to increase these bone strains, which is really the deformation in your bone that results from this loading. And those bone strains are thought to increase the amount of micro damage that accumulates in your bones. You have more deformation, you'll incur some more damage. And it's really thought that if you have more micro damage, these micro cracks and voids are probably degrading the bone quality, so it's not quite as strong. If we degrade the bone quality, those bone strains are likely to increase in the future. So if we can't resist the loading, more deformation will occur, we'll accumulate more micro damage, we'll decrease our bone quality further, increasing those strains over and over and over again. So this is kind of that positive feedback loop that I was talking about on the first slide of this presentation. And we know clinically, if we get stuck in this loop, it may result in something like a stress fracture. As I talked about, this of course isn't the whole process. So we have the bone remodeling process here as well, which gets initiated by the micro damage that's accumulated through these loading cycles. And so it's thought that bone remodeling works to go back and maybe repair some of that micro damage. So if we have less micro damage, it could be the case that our bone quality is actually increased. So we have some stronger bone. If we have stronger bone, then maybe those bone strains are reduced for the next bout of loading if we give a period of time to rest and allow the bone to heal. So over here on the right-hand side of your screen, this is kind of that situation where we have the damage rates exceeding the bone remodeling rates. So we're actually damaging the bone quicker than the bone can repair itself. And so it's thought that this leads to reduced bone quality. And then on the left-hand side of this framework, this is that situation where the damage rate is either less than or equal to that remodeling rate. So if we're able to repair quicker than the bone's actually being damaged, it's thought that we may improve that bone quality so long as that remodeling rate doesn't get too out of hand. And so this here is what you'll typically see in the literature when we're talking about how bone might respond to mechanical loading. But in fact, we do know that bone remodeling actually increases bone porosity. So it may actually decrease bone quality. And some studies out of our own group have shown that a resorption canal may actually reduce the fatigue strength of bone by 2 to 3 orders of magnitude when compared to the normal canal in that cortical bone. So whether or not this bone remodeling process actually serves to improve bone quality, maintain that bone quality, or degrade it is actually somewhat equivocal. And it's similar over here on the sides of micro damage as well. So micro damage is known to dissipate energy, so it's possible that it may actually increase your bone quality if you have some accumulated micro damage. And studies have shown that micro damage may act as a toughening mechanism, and it actually increases fatigue strength. So whether or not that micro damage itself is degrading that bone quality, improving it, or maintaining it is also somewhat equivocal. And so both sides of this generally agreed upon framework have some questions there, but we actually still don't even know what the direct mechanistic link is between this accumulation of micro damage and that bone remodeling response. And before we go on, I'd just like to draw your attention here to these bone strains in the middle. So this kind of whole framework is built off of bone strains that are right at the center of this framework. And I'd just like you to keep that in mind because we'll return to this later on in the presentation. So understanding mechanobiology and bone adaptation is very important. So mechanobiology is this means by which bone actually achieves adaptation. And what we've discussed is that that interplay between mechanical loading, the bone remodeling response, and the overall bone quality is actually somewhat controversial. And this is an important thing to note because all of our clinical decision making has really been based on these long-standing controversial assumptions of a framework that doesn't really have high-quality data to support it. So having a more mechanistic understanding of mechanobiology will inform many things, but in particular things like osteoporosis treatments and fracture prevention methods. Now, unfortunately, our progress has been a little bit limited by some insufficient animal models in developing this understanding of mechanobiology. So our current understanding has been largely based on these in vivo rodent loading models. We can see some examples there on the left-hand side of the screen. And we certainly do need more of these in vivo loading models, particularly those that are actually perturbing the natural states of bone remodeling using things like anti-resorptive drugs. But one of the big issues is that rodents don't actually naturally exhibit this intercortical remodeling that humans do. So it makes it challenging to kind of translate that knowledge that we've developed and gained in these rodent animal models to the human condition. So instead, our group has developed an in vivo rabbit tibial compression model. So compared to rodents, rabbits actually do exhibit some of this intercortical remodeling, and we can use them to study this idea of mechanobiology a little bit more in depth and maybe have some more translation to the human condition. So ultimately with this in vivo loading model, we hope to establish some of these relationships between mechanical loading, the resulting strain environments, the amount of micro damage that gets accumulated, that targeted remodeling response, and of course, the overall bone quality. And so now I'll bring us back to this conceptual framework here and recall how we were talking about bone strains kind of being at that central point, and they are super important because they kind of initiate this whole process. And it's exceptionally important for investigators who are using these in vivo loading models to have a good idea of what mechanical environment is being produced from those loading devices. And it's critical because those strains actually directly influence the amount of micro damage that's being accumulated, that targeted remodeling response, and the overall bone quality. So this is actually specifically what my work focuses on, is trying to find ways to really elucidate this mechanical environment, get an idea of what strains are being produced by this mechanical loading device, and use that to relate it back to some of these other concepts in the bones process and adaptations to mechanical loading. So what I do, I use computed tomography-based finite element analysis to capture this strain environments. This is a process that's become kind of the gold standard in the literature in our fields for quantifying this mechanical environments. And throughout the rest of my presentation here, I'll be talking pretty much exclusively about CT-based finite element analysis. So I'll briefly go through what this process looks like at a high level. So typically we start with doing some loading experiments. We'll try to capture some experimental strain data. And using that strain data, we can then go back and compare those experimental measurements to our predictions from our finite element models and hopefully validate them. We then take CT scans of those bones of interest that we've used in those loading experiments, develop our finite element models, and get those ultimate strain predictions. So CT-based finite element analysis is a very powerful approach. It's subject specific, so we can capture things like the heterogeneous material properties that are individual to each bone. We can, of course, capture the unique geometry of each bone, and those things highly influence what those ultimate strain predictions will be. So this kind of brings me to the objective of my work, which has been to develop an animal-specific CT-based finite element modeling routine to predict in vivo erratic tibial strains. And we have to address two things in order to accomplish this objective. So first and foremost, we do need a way to establish heterogeneous material properties and come up with an accurate method of doing that. Once we have those material properties, we can go about determining those loading and boundary conditions for our finite element models, and then accomplish our ultimate objective here of developing this animal-specific CT-based finite element modeling routine. So I'll start with talking about this issue of material properties. So over here on the left-hand side of your screen, we have a CT scan of some bones of interest. This is after they've gone through some mechanical loading. These are excised bones. And included in all of these CT scans, we have a CT calibration phantom. So a calibration phantom has these hydroxyapatite inserts, each having a known density. So you can imagine if we have a known density included in our CT scan, we can relate that back to the underlying Hounsfield units coming out of the CT scan. And we do it exactly like equation 1 here, so we can get our hydroxyapatite equivalent bone density values as some function of the underlying Hounsfield units throughout every single voxel in that CT scan. Excuse me. And so we see here on the right-hand side of your screen, this is an example after those heterogeneous density values have been assigned to a particular bone. And we can see there's quite a lot of variation over the entire surface, and there's certainly going to be more if we move into those trabecular regions or regions where we have kind of a thin cortical shell. But of course, for finite element analysis, we wouldn't use a material property like density. We're talking more like something of the likes of the elastic modulus here. And so we have to convert those density values into elastic moduli now. And it's been suggested and very commonly used in the literature that there exists a power law relationship between those hydroxyapatite equivalent bone density values and the underlying elastic modulus of that individual voxel. So it looks something like equation 2, and we have these unknown constant parameters, coefficient A and exponent B. So the big question becomes, well, what is that coefficient A and exponent B that we should be using? And there have been a number of density elasticity relationships that have been developed, particularly for human bone, which is what we're looking at here on the screen now. But even when we group these relationships by things like the loading and boundary conditions, the specimen geometry, or the anatomical location, you can see there's still quite a bit of scatter in these relationships. And again, this is for a human bone, but when it comes to something like the rabbit animal model, there doesn't exist any single agreed upon density elasticity relationship, even though it's a really important orthopedic model in biomechanics and is quite commonly used. So the objective of this first study then was to establish an experimentally validated density elasticity relationship that converts those CT bone density values into elastic moduli. And so we start with these excised rabbit hindlimb bones, we CT image them, segment, net to create these finite element models. And we mounted strain gauges at 6 different anatomical locations of interest, and we're able to take those strain gauges and match them up in the exact location in our finite element models. We do this using radiopaque CT markers right in that same location. And then we take those bones and we load them cyclically in uniaxial compression. We do this for about 20 loading cycles just to allow some time for any compliance effects. And at that final loading cycle, we compute the maximum and minimum principal strains. We do that for all 6 of those locations of interest across every single bone. And those are those experimental strains that we'll compare back to when we get our predictions from our finite element models. So in order to determine this density elasticity relationship, we use an optimization process. I'll take you through what that looks like. So we start with this initial guess at that value for A and B, and we use that to create our density elasticity relationship. And we assign those material properties to the bone. We can then determine our loading and boundary conditions and actually run our FE simulations to get those strain predictions and use those strain predictions to compare back to the experimental measurements. So we do a mean squared error comparison between the FE predicted and experimentally measured bone strains. This is across all 6 of those locations and all bones all at the same time. So after we compare those strains, we go back and adjust that value of A and B. And we can take that new value of A and B, bring it back into the density elasticity relationship, reassign the material properties, run the FE simulation, adjust the parameters, reassign, run the FE simulation over and over again. So it's a very iterative process. It's an optimization process. And effectively what we're doing is we're finding the value of A and B such that this mean squared error between the FE predicted and experimentally measured bone strains is eventually minimized, and then we're left with that density elasticity relationship that works best. So we did this optimization procedure across 3 different groups. Combined, we had 27 rabbit hindlimb bones. We separated these out into our tibia bones and femurs. And then under each one of these groups, we also had an optimization group and a validation group. So the optimization group was used to actually build out those density elasticity relationships, but the validation group was not privy to the optimization process. We used that group to test out these relationships and see how they perform on novel data. And then we also combined all of these tibias and femurs into one group to see if we could come up with a relationship that would work for both bones at once. And after we do that optimization process, these are the relationships that we converge to, and we can see for the optimization groups, at least they perform quite well. We're explaining up to 96% of the variation in those experimental bone strains in the tibia, for example. But of course, what's more important is to see how these relationships perform on that validation set, the novel data that wasn't included in the optimization process. So I'll take us through that now. So this is the validation of the optimized tibia relationship. On the left-hand side, we have our linear regression, and we can see that it still performs quite well. We're able to explain again up to 94% of the variation in those experimental strain measurements. In this case, we have a slope that's not different from 1, an intercept that's not different from 0, indicative of a y equals x type of relationship. And then over here on the right, we have our Bland-Altman analysis, and we can see some relatively good agreements, but we do have a bit of a bias towards under-predicting these bone strains. Now looking at the femur relationship, again, linear regression here on the left, we can see it still performs well, not quite as good as the tibia. We can explain up to 87% of the variation in those experimental bone strain measurements. And then looking over at the Bland-Altman plot, again, we have some of that bias towards under-predicting bone strains. In this case, it's actually a little bit more than the tibia. So when we combine those hindlimb bones, we kind of expect it to perform somewhere between the tibia and the femur. And in fact, it does just that. So we're able to explain up to 91% of the variation in experimentally measured bone strains. And again, we have still that bias towards under-predicting those bone strains. In this case, it falls right between the bias to the tibia and the bias to the femur. So to kind of summarize that, all of the groups that we had exhibited slopes that were statistically similar to 1, but they did all show this moderate bias towards under-predicting bone strains. And we do have to think a little bit about why that might be. And probably one of the biggest reasons why that could happen is we may have converged to a local minimum instead of a global minimum. So we went back afterwards, we ran a global optimization process, we used the dual annealing approach, and we're able to confirm that the function we optimized on is in fact convex. And so we can confirm that we didn't converge to a local minimum, and it's highly unlikely that the bias would be caused by that. And so Glenn and Alden in their seminal paper, they actually recommend adjusting for the bias under a situation like this. And if we were to go back and adjust for the bias, actually every single group, all the groups in the optimization, all the validation groups, they all exhibit a y equals x type of relationship, which is super good to see. And when we plot those three relationships together, we also see that they closely approximate one another, and we kind of use this as motivation to suggest that for situations where you may want to prioritize simplicity or computational efficiency, you could probably just use a single combined relationship for both bones instead of using those individual relationships for each one. And that brings me to some conclusions from this first study. So we established the first validated density elasticity relationship for rabbit hindlimb bones. And they provided these highly accurate strain predictions. So hopefully that'll enable a CT-based FEA for researchers using these preclinical rabbit animal models, which of course we're doing. So that's leading me right into our second study. And this is where we're actually developing a CT-based FE modeling routine, predictive tibial strains produced by our in vivo mechanical loading device. So this is where we're determining those loading and boundary conditions for the finite element models. So we started with newly euthanized New Zealand white rabbits, and we created an incision near their tibia. Through this incision, we mounted strain gauges on the anterior and posterior surfaces of the bone. And then we take the entire intact rabbit over to our mechanical loading device, as we kind of saw earlier. We take the hind limb through a few bouts of cyclic loading and uniaxial compression, measure out those strains. Again, those are used later on to compare back to our finite element models. After that, we excise the hind limbs, we take them to the CT scanner, and then use those CT scan data to develop our finite element models. And now I'll talk a little bit about the finite element modeling approach that we use. So in general, not only us, but when you look at FE studies, the general approach is to really prioritize simplicity while maintaining accurate predictions. So the idea is we don't want to increase the complexity of our models if it's not going to increase the accuracy of our predictions. You're then wasting time in the modeling process, and of course, it becomes more complex and increases your computation time. So our approach to this then was to develop statically equivalent systems. It's an approach quite frequently used in our field as well. And we can do this by just assuming a single concentrated load at the proximal end of the bone, and then we can have a fixed distal end constraint, so we have a really nice simple model that we can evaluate the strain predictions from. Now, of course, the question then becomes, well, if you're just using a single concentrated load, how exactly should that load be oriented to achieve static equivalence to what's being experienced in vivo? And what we do know is that this hind limb orientation certainly cannot be perfectly controlled or replicated. So there will be variation between experiments. There's likely variation within the experiments as they undergo load. And even more challenging, after we kind of excise those hind limbs and bring them into the CT scanner, reconstructing that position is very, very challenging. And again, probably no chance that you're going to perfectly match that orientation. And to address this issue, we propose using an experimentally informed approach. So we're doing an optimization routine very similar to that first study again. And effectively, this results in individualized load orientations for every single experiment. So we use the experimental data, determine the load orientation, and this is through an optimization process. So we're finding the orientation that minimizes the error between the FE predicted and experimentally measured bone strains. So after we do that optimization process, this is what those orientations look like here. So these are plotted over a representative tibia. And just to kind of orient you in terms of direction, We have the definitions there at the top left of the screen. So we use two angles to find these orientations in spherical coordinate system. We use an azimuth angle, so it's measured off of the posterior axis moving medially. And then we use an inclination angle, so it's measured off the negative longitudinal axis. And that allows us to define an orientation. And what we can see is that all the orientations coming out of that optimization process, they look somewhat nicely grouped together. They do all act in the same general direction. So they're in compression moving towards that anterolateral direction. And we converge to an average azimuth angle of 195 degrees. And one thing I'll point out is that there is a pretty significant deviation there. So we're moving plus minus 28 degrees across this whole data set. And for our inclination angle, we converge to 7.7 degrees plus minus 3.6 degrees. So having these individualized load orientations, we can now run those FE simulations and evaluate how their predictions perform. So over here on the left of the screen, we have, again, a representative FE model from one of those tibia bones. And we see a really familiar kind of characteristic strain distribution exactly as we would expect. So we have these tensile strains on the anterior surface. We have compressive strains on the posterior surface, distribution that we certainly expect. And looking at the strain prediction results, I mean, it performs really well. So we can explain up to 96% of the variation in experimentally measured bone strains. Again, looking at the Bland-Altman plot here, we always have this issue of underpredicting strains by some amount. So we can say that this approach works quite well. We get accurate strain predictions. It's certainly a useful method, but kind of in the spirit of trying to simplify these models as much as possible, it's still useful for us to know whether or not a single assumed orientation across all bones can actually work as an approximation. Again, trying to simplify these models as much as possible. And so in order to determine if that can happen, we first need to evaluate how sensitive those strain predictions are to changes in that load orientation. So here on the right-hand side of your screen, we're looking at a polar plot. These are all those individually oriented force vectors. So going around the circumference, we have those azimuth angles. In the radial direction, we have the inclination angles, so we can define all those orientations in this polar coordinate system. And this is bounded by plus or minus 2 standard deviations in that average azimuth angle that we talked about a couple of slides ago, and the average inclination angle as well. So we get this colored region here, where we would expect 95% of those loads to be oriented, at least with our experimental data here. And what we do see is there's a very, very strong error gradient across that plus or minus 2 standard deviation bounded region. And in fact, we actually never get below 800 microstrain of error. So it's going to be very challenging to use this. In one case, just from an example of a bone, just changing that orientation by 9 degrees resulted in a difference in predictions by 90%. So it's very, very, very sensitive. But nevertheless, it still is interesting and useful to compare how these approaches may perform against that individually optimized approach. So we looked at evaluating 4 different single orientation techniques. We used the purely vertical loads. We used the average orientation coming out from a couple of slides ago. We used the error minimum orientation, so finding the minimum from this plot and using the orientation at that point across all models. And then we used an error-weighted most probable orientation. So the idea is that we could use maybe the error minimum, which of course is going to result in the least amount of error, but it's definitely not going to be the most probable orientation for a new bone loading experiment. So if we weight the most probable orientation by the error, we can kind of find a balance between using the minimized error and the most probable orientation. And one thing I will point out is using a purely vertical load across all models is actually the most common approach and almost exclusively what you'll find in the literature in our field. So taking us then to the next slide here, looking at their performance, if we use a purely vertical load, we get errors all the way up to 3,400 microstrain. So in terms of relative to the strain that the actual bone is experiencing, that error is probably triple what the bone is actually experiencing in vivo. So that purely vertical load certainly isn't working great. When we look at the average orientation, that doesn't seem to work great either. We can only explain up to 38% of the variation in experimentally measured strains. We still have high errors in that 800 microstrain region. And similarly, for that error-weighted most probable orientation applied across all these models equally, we still have high errors in that 800 microstrain region. We can explain a little bit more of that variation of 42%, but actually using this error-weighted most probable orientation or the error minimum orientation or the most probable orientation, they all perform just about the same. So this kind of brings me to some conclusions from this work. We use optimizations to determine these individualized force vector orientations, and those resulted in statically equivalent systems. So they reproduce the strain environments that was engendered in vivo. And the models with those individualized force orientations performed well in terms of strain prediction. So explaining up to 96% of the variation in those strain measurements, but then using a single assumed orientation actually increased those errors by 2 to 3 orders of magnitude. So it'd be very challenging to assume a single orientation across all of these models. Now, one thing that we do recognize is that it's not always feasible or possible to use an experimentally informed approach to developing these FE models, particularly for in vivo studies. So there may be ethical or logistical constraints to mounting strain gauges on a bone while the rabbit is alive. And so we do have some future work to try to address this, and it will become important for our work too. So I'm currently working on developing a probabilistic strain distribution so we can get kind of a general idea of what magnitude of strain a typical bone will be experiencing. And the way we do this is we create a statistical state model of the rabbit tibia, and then we can map the strains from each loading experiment back onto that average shape. So we get an average idea of the strain response in the anatomically relative location for each in vivo loading experiment. We'll then look to validate these strain predictions using a 3D load cell. 3D load cells are quite expensive, so most researchers don't actually have access to them. We recently purchased one when we were constructing this in vivo loading device, so we'll go ahead and use that 3D load cell to validate the load orientations coming out from this optimization process. And then finally, we'll look at kind of optimizing on the neutral axis of bending. So I've talked a lot about these statically equivalent systems. So we kind of make some assumptions, but still produce the expected environment that's being produced in vivo. And we're quite confident that that's taking place, but something that would increase that confidence is if we can check the neutral axis of bending at maybe 2 different cross sections of the bone, we can then be confident that that strain behavior in the distribution has been captured quite accurately. So it just increase our confidence in the method that we've employed here. And so with that, it brings me to the end of my presentation. So thank you all for listening, and I'll gladly welcome any questions.
Jonah, nice presentation. You kind of in your introduction, you explained that there are a bunch of like a lot of variation, like human bone values and things like rodent models. Is that why you chose to do rabbit models? Because there's like no studies done on rabbit either. So what about when like other people do it, they do the same, you know, discrepancy.
Are you talking about the animal model specifically or with the FE modeling process?
Kind of with the elastic model.
Oh, yeah, okay. Yeah, there is a lot of variation. Some people use different approaches. There are different ways to actually capture the material properties. So typically for rodent studies, they'll use higher resolution imaging. We actually use clinical CT. So if you use clinical CT, you certainly do need to use a density elasticity relationship. And I mean, even as we've talked about, we all acknowledge that there is quite a bit of error in that process. So it's just something that needs to be acknowledged as a limitation. But using that optimization procedure, at least we know that the relationship we're using has been built specifically for the conditions that we're simulating. Other people will use that high resolution imaging. And so if they stick their bones into maybe a micro CT, they actually don't really need to assign heterogeneous material properties because they can resolve the size of the pores that exist in the bone. But a lot of times, it's actually the pore size that's contributing to that difference in density throughout those Hounsfield units in the CT scan. So for rodent animal models, they don't quite need that, and that's why we had to develop it as we move into these rabbit animal models.
The elastic model that you calculated and explained, they are the axial space, just not isotropic pop, and it's not an isotropic material. So it's just,
Yeah, you're right. We don't have an anisotropic material model here. It's again one of those limitations. So we probably would underpredict something like a bending loading regime. Certainly the case, but we do all of our experiments in the axial compression. So we're most concerned about that axial modulus. And as far as we can tell, it doesn't have a huge effect. I know some people from our group have shown that actually including that anisotropy is quite important. So it's certainly something that we should look at in the future. But again, we still get some really great strain predictions using simplified isotropic material models. So in that spirit of not trying to increase complexity where we don't have to, particularly when we do this big optimization process, I mean, we can throw it up and wait for months before we get a result, right? So trying to simplify those models down as much as possible is super, super important for us. And that's why we go with the isotropic model.
Matt and then Art.
Your blind Alden plot, it looked like there was some heteroskedasticity. I think that's but it, so I was looking at the x-axis, seeing sort of how the error or it's changed across the measurement. And I noticed it goes from like negative and then there's zero, then it goes to positive. Can you explain a little bit what, like, just simply like what does that reflect, the negative to the positive value, and why the error kind of just gets a little bit bigger there?
Yeah. So maybe I'll talk first in the linear regressions when you see it crossing from those negative values to the positive values. That's mostly because we're doing this on both maximum and minimum principal strains. So our minimum principal strains will always be negative values. Our maximum principal strains are usually positive values unless we use the absolute value from the strain. So that's why we cross zero there in the linear regression. For the Bland-Altman plot, it's kind of tough to say. Probably one of the reasons why we don't have a perfectly horizontal slope in those plots is that as we increase the strain magnitude, it's more and more challenging to predict that strain. So particularly when we look at those femur models, one of the big challenges is the femur has a lot of curvature in it. So the strain that it experiences is quite a bit higher than what we would see for the tibia. That's a really straight bone because it's bending quite significantly. So you start to see a trend in that Bland-Altman plot when you have increased bone strains. It's more and more challenging to predict because you start to get into a region it's maybe less linear than we would hope it to be because a lot of bending is taking place. So if I were to guess, that may be why, but yeah, it's hard to say.
You showed a bunch of plots from other groups showing, I guess, modulus versus density. And then you calculate your own numbers. Where do you sit relative to those other plots?
Yeah, there's no real direct comparison because all those relationships have been developed for human bone. And all those relationships have been developed using small machine samples. So nobody's actually done this using computational methods. And that's important for us because we're using this in epi models. People will use density elasticity relationships for other research studies, for other purposes. And typically when they develop those relationships for human bone, they'll take a small machine sample, they'll measure the density, like they'll actually do a density measurement of the bone. So they'll maybe take like the abstraction and get the true density of the bone, and then they can measure out the elastic modulus through the mechanical test. So that's how they develop those relationships. They take a bunch of machine samples, measure the density, get the elastic modulus from the mechanical test. They do destructive testing, and they can develop those curves. They curve fit it, and then that's the relationship they get. Our relationship is quite different from that. It's a different bone. It's a rounded bone. We're looking at the whole bone, not a machine sample. And we're doing it strictly through computational methods, not experimental methods. So it's really hard to say. There's really no direct comparison, I guess, is what I'm saying. It's for a completely different purpose on a completely different species. So as long as it gives you relatively good strain predictions, we feel confident using it, and it's improved other models from our group in the past as well by using one of these optimized relationships.
I think I only agree with you on half of it. Okay. So
Which that?
for sure, that coefficient A, that's going to be a different number for every experiment, and it's really hard to compare those numbers. But exponent, if it's based on you know, if you say bone has pretty standard mechanics for compression, an exponent is something worth comparing. And then you don't need the, so you can divide out the coefficient, then you just compare purely the exponent. So that's actually what
You're
interested.
Yes, you are right. So, our exponent, so when we went back into that global optimization, the way we determined our bounds for that optimization was doing exactly that. We determined it off the exponent. So from those, human studies, the exponent that you'll get from the relationship is somewhere between 1 and 4. And our relationships do fall within that range between 1 and 4. But that's how we kind of use to bound it. Yeah, you can have a huge difference in that coefficient. So the behavior of the relationship is quite similar, and then it's going to be shifted off a little bit. So yeah, I mean, it's comparable, but if you go from a coefficient of 1 to a coefficient of 4, that's quite a significant difference in behavior, right? So while it's in a relatively small region, the actual resulting behavior isn't quite similar. So yes, we can assume that bone relatively has similar mechanical properties across the bone, but in fact, most research suggests that that's not quite the case. And there's a whole host of reasons why that might be true. So it's challenging to compare these to one another. And that's why we think these kind of experimentally informed approaches are very important in bone studies.
And do solid mechanics people say anything about what the exponent should be?
Not that I know of. Most have been developed as purely experimentally, so I'm not sure.
Well, if it were based purely on mechanics, I think, well, you might ask self authority.
Yeah.
But usually the number is just an integer. So that's just because of whole stuff like.
Yeah, the analytical solutions, yeah.
And so that would be the usual expectation. And then I would guess that someone like Salvatore would actually say, oh, well, if you assume this, then the number should be 3 or 2 or something like that. Wondering what they might say.
Those certainly could be true. On the continuum mechanics side, not a whole lot of people are looking into these relationships. A lot of times they're just, I mean, they don't typically care about the underlying density values. We only care about it because we're using the CT values, so we need it in order to get our elastic moduli. For a continuum mechanics person, they're just going to develop their relationship straight from the elastic moduli themselves, right? So,
Well, from the elastic moduli of the underlying material, what you're talking about is the structure, right? So I mean, I'm agreeing with you, but I'm just saying that if they're developing from an elastic modulus, they're talking about something at a lower level than what you're.
yeah, sure.
You want to know something about loading of bone. You know that bone has different types of bones, cementless and foot. So when somebody talks about loading of bone, I always expect that one would make a difference or a distinction between these two different bones, and that the results would show that difference, which in your case they didn't. So why do you not have to do that?
So are you talking about the difference between like trabecular and cortical bone?
The loading of, if you load the bone, the trabecular bone will have different loading than cortical bone.
Certainly. So that's one of the assumptions we make. So whole bone mechanics is quite complicated exactly because of that. You know, you have different types of bone. Porosity is going to be different. The underlying mechanics are certainly going to be different between the trabecular regions, the more cortical regions, those transition regions as well. And one of our assumptions is that, you know, we can really simplify this down and still maintain really accurate strain predictions, just assuming kind of a continuum approach and hoping that that underlying density elasticity relationship kind of accounts for maybe the reduced elastic moduli in that trabecular region where we have more porosity. So it's one of the assumptions we make. It's hard to tell, but what I can say is we still get good strain predictions without trying to separate out the cortical and the trabecular regions. And that's kind of all I can say on the topic. It's, some people, particularly if they're doing more high resolution imaging, they're able to capture, the actual microarchitecture of the bone. For us, we can't capture that using clinical CT. So we really don't have much of a choice, but to kind of assume that this is a continuum model, and we don't model those pores in place. We just hope that that shows up in the resulting elastic modulus, so we'll be a little bit less dense.
I don't think it's good.
I actually think it's working. I mean, we get great strain predictions, so if we don't need to model the trabecular regions.
Is it important that difference between the bone?
It's certainly important. It's something that if you were using a different modeling approach, it needs to be considered. Here, we would suggest that it doesn't need to be because we can still maintain those predictions. And again, I kind of go back to our whole goal is to maintain simplicity. We want to make these models as simple as possible because we use them in further computational methods like optimization. These highly iterative methods really stack non-linearly in terms of computation time. So if we start to separate out things like trabecular bone and cortical bone, we increase the complexity of our models, and then we throw it into an optimization process, and suddenly I'm here for a whole PhD before it actually converges, right? So that's kind of our goal. It is something that's important, I agree with you, but if we can still get great accurate strain predictions, we're particularly interested in cortical bone, so the region that we're looking at these predictions, we actually don't really ever look at those trabecular regions. We only look in the cortical regions anyways, but certainly the trabecular regions will influence the strains that get produced in the cortical regions. So it's definitely important, but all we're saying is that using this simplified approach, we still get good strain predictions. So, you know, what's the need, what's the purpose to increase this complexity if it's not super necessary?
Question, Venus? Are you using porosity and density interchangeably? Like, what I mean is that porosity, so, okay, those holes, and then density, you're looking at the macro structure, like, okay, the hole, but what about the quality of the bone itself?
Yeah.
Like, if there is remodeling, maybe you have less, I don't know, calcium or some hydroxyapatite, stuff like that. So, what are those like, is porosity predictable of the norm of the
I don't have the answer to that question. So I do kind of use it a little bit interchangeably. What we can say kind of qualitatively, if you were to look at one of these CT scans and you go into that trabecular region, you will see CT voxels that have lower gray values, so they're less dense. And when I talk about density, some of the thought is that, well, if you have more porous material that underlies it, it will scatter those X-rays more, and then we're not going to get as dense of a value on the other end. So the thought is kind of, well, you know, if you have poor microarchitecture, we can't capture that with the resolution that we're scanning at, but it will probably result in lower density coming out of the CT scan because those X-rays are passing through a little bit easier. And so it kind of affects the macro scale material properties. And that's sort of why I use the term interchangeably, but it's not something that we can actually capture in our model. We can't capture any microstructural properties.
So do you think that during remodeling, the quality of the bone independently of porosity will change as well?
That's a big question. It's actually why we're doing this work now. And hopefully soon we'll figure that question out. We don't know. And that's why I was talking about this kind of framework that everybody bases these clinical decisions on. But we really don't know. A lot of people would suggest that if bone remodeling is actually increasing the bone quality, despite the fact that new canals are being created. But a lot of people, and actually our group kind of disagrees with that. We think that those pores actually contribute to decreased bone quality, so the actual overall strength. I don't know if it's independent of one another. I don't know what the causal mechanism is, and actually, as far as I can tell, nobody does, and it's why we need to continue on with these studies and specifically look at intracortical remodeling for that exact reason.
Jonah?
I was wondering why you chose the loading condition that you did, because it seemed, I mean, so as you said, it's really difficult to say what the actual orientation is And it strikes me that that's just a very difficult condition to try to load straight down the bone. So why was that?
It actually experimentally is the easiest way to do it. You could do things like a 4-point bending, but ultimately what the literature has kind of moved towards is what they call these non-invasive compression models. So they don't want to, create an incision in the bone or create an incision in the soft tissue, set up their 4 points to do a bending test. They really want, particularly for in vivo studies where the rabbit's only going to be anesthetized and then allow time to heal. If we do something like a 4-point bending test, we'll really damage the soft tissue in that region. And so the literature has really moved towards this kind of quote unquote non-invasive axial compression method. But yeah, it's not an easy thing by any means. And as we see, it produces a lot of challenges that we have to deal with.
So did you do the mechanical testing for the scanning?
Yes, yeah, we did.
So what are the parameters in your loading? So are you still within the limit of not damaging damaging
Yeah.
the bone because you're gonna scan impact?
So there's two things that we do. We try to make sure that the load magnitude that we apply will still make sure that we're in that elastic region, so we're not plastically deforming the bone. We do know that damage can accumulate in kind of a fatigue regime, so even in that elastic region, you can incur damage. It's certainly possible. We try to limit the number of cycles of loading, so we do 20 cycles. Ideally, we would just do one bout of loading, but there is kind of, particularly when we go to the in vivo rabbits, there's a lot of soft tissue compliance for the potted bone samples, for example. There's a lot of compliance between the potting material too that has to settle a little bit over the first kind of 10 or 20 cycles. So that's why we do 20 loading cycles, but we try to keep that number as low as possible to not affect the bone quality in those CT scans. Yeah, we just do the best that we can, but it's a limitation for sure, but we have to load before we scan usually.
This would make your study complicated. And the first one, the in vitro, so did you try like scan and then?
In those, they were scanned before, yes, but for in vivo, no. Yeah.
Let's make a suggestion about your loading, which is maybe you should intentionally do it wrong.
Okay.
So I'm assuming at the bottom you're doing some sort of fixed. Okay, so it's fixed. So then you can sustain moments there. So rather than trying to go straight down the bone, intentionally go in a direction that you're going to, I guess, opposite to where your strain gauge is. So then you're going to maximize your compression. And so you're already fixing the bottom. So you already, in a sense, have half of a 4-point bending. Then just by introducing that bias, your loading is going to be roughly the same, but then you have a lot of uncertainty due to things like the curvature and stuff like that. And so the amount you want to be off is enough to compensate for that weird shape of the bone and the curvature and things like that.
Yeah, exactly. And this will be a much easier process to do with our 3D load cells. So we can adjust the loading. Actually, the new in vivo loader is fully adjustable, so we can change the axis of loading completely. And we can do that to kind of cancel out stock axis loading from our load cell if that's the way we wanted to do it. So yeah, in the future, it's certainly something that we'll be looking at.
So the next step in this, now that we've developed kind of the methodology and validation, that you're able to predict strength well, is the next step now to look at whether that remodeling or damage condition is actually affecting the quality of the bone.
Yeah, that's right. So studies currently ongoing now. One of the postdocs in our group, Tomo, he's working on that. So this is just the mechanical environment portion of that project, trying to see if we can get some accurate representation of the strain distribution. And then in his study, this will be used to kind of correlate those regions of high strain with things like microdamage accumulation and hopefully the remodeling response too.
Any other questions before we thank Jonah for his talk today? Yes.
So he said that the osteoblasts, they produce
don't know if it gets mineralized based on the load, we're not sure, but during that initial pass of the cutting cone, the bone matrix is not fully mineralized, so it takes some time for that mineralization to take place. Whether that's dependent on loading, it's really hard to say. That's another one of these big questions that people use these in vivo loading models for. So they try to study the bone adaptation more on the bone modeling side. So in producing more bone in response to these loading conditions, that's where a lot of this work has been focused on. Yeah, we don't know. We're not sure.
Very ignorant question. Micro thing.
Mhm. Yeah.
Can you use the percentage?
It's essentially a percent, so it's just it's the ratio of the change in length to the overall length, for example, if you're looking at an isotropic voxel. So if we just 10 to the 6, yeah.
Perfect, let's thank him and let's wish him good luck for his defense coming up very soon.